Okay, 2001 HSC paper question 1. A person has a mass of 70 kilograms. What is the weight of the person at the Earth's surface? Now, at the Earth's surface, we already know that acceleration equals 9.8 meters per second squared. We've got F equals ma, so that's 70 kilograms times 9.8 meters per second squared, and that would give us 686 newtons, not 686 kilograms, because force is in newtons. 2002 HSC paper. The table shows the value of acceleration due to gravity on the surface of Earth and on the surface of Mercury. So Earth's acceleration is 9.8, Mercury's acceleration due to gravity is 3.8. So if we quickly find the percentage between these two, we're going to get 3.8 divided by 9.8 times 100, so that's around 38.8%, 39%. A person has a weight of 550 newtons on Earth. 39% of that would give us the weight on Mercury, which is 213 newtons. 2003 HSC paper. The weight of an astronaut on the moon is 1/6 of her weight on Earth. What is the acceleration due to gravity on the moon? Very simple. A equals 9.8 meters per second on Earth. The moon is just going to be that divided by 6, which is B. 2008. An object on Earth has a weight of 490 newtons and it experiences an acceleration due to gravity of that. We already know that's the acceleration on the surface of Earth. On Mars, this object would experience an acceleration due to gravity of 3.7 meters per second squared. It's saying what would be the weight on Mars. So first we have to find the mass of the person. F equals ma, or in other words, m equals F over a, which is 490 newtons over 9.8, and this would give us a result. This would give us the mass. If we just multiply the mass by the acceleration, we're going to get the force that the person feels on Mars. So all we have to do is multiply this by the acceleration on Mars, which is 3.7 meters per second squared, and we get the force that they feel on Mars. 2007 question 4. The acceleration due to gravity on Earth's surface is g. Suppose the radius of Earth was reduced to a quarter of its present value while its mass remained the same. So what formula are they talking about? G equals big G, big M over d squared. So they're just saying if we reduce d to a quarter, what we're going to get is 1/4 squared, which is going to be 1 over 16. So that means this formula is going to be gm over 1 over 16, which is just going to be 16 gm, which is going to be 16g. So that's question 4 answered. 2006 question 1. Given that g is the universal gravitational constant and g is the magnitude of acceleration due to gravity, which statement is true? The values of g and g depend on location. No, this never changes, this does. So C would be the correct answer. Big G is the same everywhere in the universe, but small g is not. Last question, 2004 HSC paper. The diagram shows two planets X and Y of mass m and mass 4m, respectively. It's saying at the distance d from the center of planet Y, over here, the acceleration due to gravity is 4 meters per second squared. What is the acceleration due to gravity at distance d from planet X? Very simple. The gravitational acceleration for Y over gravitational acceleration for X equals g 4m over d squared all over gm over d squared. They cancel out, so you're left with the ratio of 4. So the gravitational acceleration of planet Y is 4 times more than X. But it's saying, what is the acceleration? We know that the acceleration of acceleration gy is equal to 4 meters per second squared. So this means 4 meters per second squared over gx equals 4 Therefore G equals 1 meters per second squared.